Good morning, everyone. Lesson 3 in our matter unit is on attractive forces. Attraction, so two things pulling towards each other, or multiple things pulling towards each other. So we mean by attraction. We use it a lot in common language when we think of the attraction between two humans, and the pull that drives those two humans together. Learning objective is I can illustrate and describe the forces that hold matter together. It is these attractive forces that hold it together. Quick review from yesterday, though. Draw the states of matter you see below, or label the states of matter you see below. Add arrows to indicate how the molecules would be moving if it was a video rather than a picture. Pause the video for a moment and go ahead and add in some arrows to these. Come back in a minute or so after you added some arrows as to how they would move. Think back to the simulation yesterday when they were actually moving, and add in arrows that you think would depict that. So pause now. I've assumed you paused it and you've returned to me. So this is a solid, this is a liquid, and this is a gas. The particles of the gas are the fastest moving. I'm going to draw nice big arrows because they move very fast. They bounce off of one another. They bounce off the walls of their container. Lots of movement. Lots of kinetic energy. Liquids, they move a little less so, but they don't escape into the gas above, generally. That is evaporation, which is a special circumstance, but generally our liquids, they just flow past each other. So I've got these kind of winding arrows showing, yep, we got some kinetic energy, and they kind of slide past each other. Solids, don't be fooled. Solids move. At the molecular level, they move. And from the sim yesterday, you saw they were just vibrating. And the hotter you got it, yet still solid, the faster they would vibrate. So I'm doing these kind of back and forth arrows to show that the little atoms that make up this solid substance, they just go back and forth and back and forth and back and forth and up and down, and they just vibrate around. But they don't trade places. If they traded places, that would make them a liquid. If they could totally get away from their neighbor, that would make them a gas. All right. The next bit. What is holding these gases, liquids, and solids together? In particular, gases are not being held together, right? So in particular, we're thinking about what holds our liquids and solids together. We can put our foot through most liquids, but we can't put our foot through a solid. We can put these into 3 categories. In chemistry or physics, we can definitely make larger categories for these forces, but they're like smaller, more narrow. Sorry, not larger, smaller categories. We're going to keep it broad. And we're going to go from the smallest level to the largest. Your subatomic forces, it's actually really subatomic. The attraction between protons, neutrons, and electrons in an atom. Right, so it's what's holding the nucleus together. Your protons and your neutrons are found in the nucleus. Why are they found only in the nucleus? Well, it's the atomic forces that keep the protons and neutrons together in that nucleus. Electrons, well, they're found out in the cloud. So what is keeping those electrons, while not orbiting? They've got that weird slushy wave-like, particle-like behavior, but what is keeping them there instead of just flying off into space? That something is the atomic forces. If you dive deeper into these for fun now or later, you'll learn about strong nuclear forces, the slight positive-negative attraction between protons and electrons, yet not much as enough of an attraction to make them just slam into each other. It's pretty cool. Next, intramolecular forces. What I want you to do is underline the word intra, underline the word inter. Let's define that so you can remember these two apart from each other. Intra means within. So it's within the molecule. These are the forces of attraction that are within a single molecule. So these forces, see, attraction, attraction within a molecule. So this is atom to atom. Again, in a molecule. All right, so the easiest one here is the idea that you have H2O, so you have an oxygen covalently bound to a hydrogen. These intramolecular forces, that's these solid guys right there. It's the attraction of this hydrogen to this oxygen, this hydrogen to the same oxygen. That attractive force that keeps hydrogen and oxygen together, and this hydrogen and the oxygen together, that is your intramolecular force, the attraction within a molecule, right? Because we could trace around this and say, oh, well, here is our molecule. And those highlighted lines, those solid lines, are within that black molecular space that I outlined. Let's define inter. Inter means between. So these are the forces of attraction between molecules. Attraction between molecules. So this is molecule to molecule. To do this, I'm going to have to add another water molecule to this here. We'll add another oxygen with its two hydrogens. Still going to keep its unpaired valence electrons shown up top. Again, I'm going to outline it to show where this molecule of water, its space, kind of ends. We'll highlight, again, the intramolecular forces. Those, again, are the solid lines between atoms within this H2O molecule. But now let's add the intermolecular forces. So now we're down here, the forces between. What is going to hold this water molecule together with this water molecule? To do that, we're going to do dotted or dashed lines. I'm going to do dashed 1, 2, 3. So typically 3 dashes, but you might see it as like this kind of thing. You might see it as many dots. You might see it as dashes. Doesn't really matter. They're all just common conventions for showing intermolecular forces. There's your intermolecular forces. And there's your intramolecular force. right? This intermolecular force would exist when it's a solid or a liquid. They would not exist when it's a gas because the water molecules would just be bouncing off each other as a gas. Take a moment, make sure those are copied in. Let's go to the next. Tiny little bit to wrap this up. Breaking or establishing attractive forces. So, in order to break, if you were to break, or alter, or make, whatever, your intramolecular force, just like this right here. If you break that intramolecular force, you don't have the same compound anymore. You now have hydrogen, which will actually exist as H2, and you'll have chlorine, which will exist as Cl2. These are not the same compound. Hydrochloric acid versus hydrogen gas and chlorine gas separately. It's not the same molecule, so this will be a chemical change. The chemical formula has been altered. It used to be HCl, it is now H2 and Cl2. We'll dive a little bit deeper into chemical versus physical soon. This is just an early primer on it. This time, in this image down here, you can see the bonds between hydrogen and chlorine are still there. Bonds between this hydrogen and chlorine are still there. So you still have a hydrochloric acid here and hydrochloric acid here. You're just missing that dotted dashed line between. So this time we saw intermolecular forces being broken in this case. This will result in a physical change. The presence of this intermolecular force must mean that this is solid or liquid hydrochloric acid. Whereas this, if there is none over on the right side, it must be a gas. Last piece here. Just wanted to quickly point out the strength of these attractions. Your intermolecular forces, the ones between the molecules, those are the weakest. So as you add energy to a substance, usually you're going to go through phase changes. Go from solid to liquid or liquid to gas, long before you alter the much stronger intramolecular force. Your intramolecular force, those bonds within an atom, well, if you continue to dump energy in, you might be able to break those too. What are those? Well, got your covalent bonds. Ion to ion, the key, that's ionic bonds, right? Ionic bonds is a cation to anion. Finally, and the hardest one to break because it is by far the strongest, your atomic forces are stronger than everything else. So, intermolecular forces break first because they're the weakest. Intramolecular forces break next because they're stronger than the intermolecular forces, and atomic forces are the hardest to break. Atomic bombs. Last, if you want, I would love you to do a quick little internet research. What is a phase change? What are all the names of the phase changes? You'll be more ready for tomorrow. And then go on over to Classroom. Open up the plan. Actually, you don't even need to open up the plan. In a moment here, I will have homework 4.3 posted. And it's just a quick 3-question Google quiz for you to test your skills from today's lesson. Adios, everyone. Take care.